This is literally everything about discrete mathematics. The counting, the logic, the graphs, the codes, all of it. And I want to spend some time with you tonight tracing where it all came from, how it grew, and why it quietly became the skeleton underneath the entire digital world. So get comfortable. This is going to take a while, and that's exactly the point. If you've ever taken a discrete math course in college, there's a decent chance you left with the impression that it was fine, probably useful, definitely drier than you hoped. A lot of truth tables and set notation and maybe some graph theory you weren't quite sure how to apply. I want to offer a different frame tonight because what discrete mathematics actually is, underneath all those textbook exercises, is something almost shockingly old and alive. It's a way of thinking about the world that humans discovered independently on 4 different continents, encoded in poetry and mythology and music long before anyone called it mathematics, and that now runs inside every device you own, every network you use, every encrypted message you send. So let's start there with the word itself, discrete, not discrete with an E at the end, which means subtle or tactful, discrete with an A, which means separate, distinct, individual, made of pieces that don't blur into each other. And that distinction from its continuous cousin is the whole ball game. Think of it this way. Calculus is about pouring water smoothly into a glass, a continuous flow, an unbroken stream, quantities that blend seamlessly from one value to the next. Discrete mathematics is about dropping marbles into a jar, one at a time, countable, separate, click, click, click. There is no marble number 2.7. There's marble 2, and then marble 3, and the gap between them is real and permanent. You can't slide across it. You have to jump. That distinction between flowing and jumping, between smooth and stepped, sounds simple, but it's one of the most consequential divisions in all of mathematics. The universe of continuous things gave us calculus, classical physics, the mathematics of waves and fluids and motion through space. The universe of discrete things gave us something else entirely. It gave us counting and logic and the structure of information itself, which, it turns out, is the universe your phone lives in. Now, the story we're going to tell tonight stretches across something like 20,000 years. And I find it genuinely comforting that the impulse to count and arrange and reason about discrete objects is so deeply human, because it means that every time you've ever organized something, sorted something, tried to figure out how many ways a set of things could be arranged, you were participating in one of the oldest intellectual traditions our species has. So let's go back to the very beginning. Picture a river in Central Africa, the Rift Valley, somewhere around 20,000 years ago, give or take a few millennia. A person is holding a bone and they are making marks on it. Deliberate, careful marks, notches, cut with a stone tool into the surface of the fibula of a baboon. This bone was discovered in 1950 near the town of Ishango on what is now the border between the Democratic Republic of Congo and Uganda. It's small. You could hold it in one hand, and on it, arranged in 3 columns, are a series of notched lines grouped in specific patterns. One column goes 11, 13, 7, 10, 19. The next column goes 3, 6, 4, 8, 10, 5, 5, 7. The third goes 11, 21, 19, 9. The specific significance of these groupings is still debated by researchers. Some see arithmetic progressions, some see records of a lunar calendar, some see early prime numbers. Nobody knows for certain what the person who made them was tracking or why. But here's what we can say with confidence. Whatever they were doing, it required thinking in discrete units, not smooth quantities, not flowing measures, marks, separate marks, one thing, then another thing, then another. The intellectual act of treating the world as made of countable pieces, that act, that single gesture of carving a notch to mean one thing, is the first move in discrete mathematics, not a formula, not a theorem, not a proof, just the recognition that some things can be separated and counted, and that you can represent them with a mark. And here's the thing that stays with me about the Ishango bone. The oldest known mathematical artifact on Earth is not a measurement, it's not a shape, it's a count, discrete from the very start. Now let's come forward a few thousand years. Because humanity didn't just count things. Eventually, we started asking a more interesting question, not how many things are there, but how many ways can things be arranged? That shift from counting objects to counting arrangements is actually one of the deepest conceptual moves in all of discrete mathematics. And it happened in a place and a context that I think is one of the most beautiful stories in the entire history of mathematics. We're going to ancient India, roughly around 200 years before the Common Era. And the person I want to introduce you to is not a mathematician in any professional sense. He was a scholar of Sanskrit prosody. His name was Pingala. If you've never heard that name before, that's about to change. Pingala was working on a problem that, on the surface, sounds like it has nothing to do with numbers at all. He was analyzing the rhythmic structure of Sanskrit poetry. Sanskrit verse is made up of syllables that are either long or short. Long syllables take twice the time to pronounce as short ones. In Sanskrit, the long syllable is called a guru, meaning heavy, and the short one is called a laghu, meaning light. So when you're composing a line of Sanskrit poetry, you're building it out of a sequence of these two kinds of beats, long and short, heavy and light. And Pingala asked a question that sounds completely musical and poetic, but is actually a question about combinatorics, the branch of discrete mathematics that counts arrangements and possibilities. His question was, how many different rhythms can you build with a given number of syllables? If each syllable can be either long or short, I genuinely love this part of the story because the answer looks completely mundane until you realize what it means. With one syllable, you have two rhythms, long or short. With two syllables, you have four, long, 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 short, short, long, short, short. With three syllables, you have eight. With four, 16. With n syllables, you have 2 to the power of n possible rhythms. Pingala was basically asking how many different drum patterns can you make with two types of beats, and in answering it, he independently discovered binary numbers, not as a computational system, not as circuits or signals, but as a language for describing the structure of poetry. Long equals 1, short equals 0. Every possible rhythm maps perfectly onto a binary string. The mathematics that now encodes every photo you've ever taken, every word you've ever texted, every song you've ever streamed, was discovered in a treatise on Sanskrit meter in ancient India. Think about what that implies for a moment. Pingala wasn't building a computer. He wasn't thinking about information theory. He was trying to categorize the possibilities of poetic beauty, and in doing so, he found the same mathematical structure that Claude Shannon would identify in 1948 as the foundation of information theory. The same structure your phone uses right now, 2,000 years before Shannon, 2,000 years before transistors, in a grammar text. That is the kind of discovery that makes you feel like certain ideas are just hovering in the air, waiting for someone who asks the right question to reach up and find them. And here's what's even wilder. Pingala's work didn't stop at binary numbers. In his analysis of how to count rhythmic combinations, he described a triangular arrangement of numbers, each number formed by adding the two numbers above it. He was working with the exact structure we now call Pascal's triangle, not as a geometric curiosity, but as a practical counting tool for Sanskrit poetry. He got there approximately 1800 years before Blaise Pascal was born. Let's step sideways in time and geography, because while Pingala was mapping the mathematics of sound in India, other cultures were finding discrete structures in completely different contexts. In China, around 650 years before the Common Era, there is a legend, and it's clearly a legend, but it's the kind that mathematical historians find genuinely interesting because it encodes something real. The legend says that a great flood was ravaging the Yellow River, and the mythical Emperor Yu was working to control it. During his labors, a turtle emerged from the waters, and on the turtle's back was a pattern, not decorations, agreed, a 3 by 3 arrangement of dots, 1 through 9, where the numbers were arranged in a precise way, such that no matter which row you added up, no matter which column, no matter which diagonal, the sum was always 15. This is the Loshu square, the oldest known magic square. That remarkable object in discrete mathematics, where a grid of distinct numbers is arranged so that every row, column, and diagonal sums to the same value. What makes it genuinely interesting beyond its mythological wrapper is this: the person who laid out those 9 numbers was doing something that belongs squarely to discrete mathematics, not measuring a continuous quantity, not calculating a rate of change, arranging a finite collection of integers and reasoning about their combinatorial properties. And the fact that this was considered significant enough to weave into a founding myth tells you something about how deeply these discrete patterns resonated. Numbers arranging themselves into perfect symmetry, every path through the grid leading to the same destination. There's something deeply satisfying about that. Now let's move to Greece, because the Greek contributions to discrete mathematics come in two very different flavors. The first is philosophical, Aristotle, who lived from 384 to 322 years before the Common Era in Athens, was not primarily a mathematician. He was a philosopher in the broadest sense. Biologist, logician, literary critic, political theorist. He had a voracious, almost compulsive need to categorize and systematize everything he encountered. And one of the things he systematized was the structure of valid reasoning itself. Before Aristotle, logic, the study of what conclusions follow necessarily from what premises, was largely informal. People made arguments. Some arguments seemed better than others. But there wasn't a general theory of what made an argument valid. Aristotle built one. He developed what he called syllogisms, a formal system for deductive reasoning. The classic form, all humans are mortal. Socrates is a human. Therefore, Socrates is mortal. That might seem almost childishly simple, but Aristotle formalized dozens of different valid argument forms, named them, classified them, and showed which inferences were genuinely compelled by their premises and which were not. In doing so, he essentially invented formal logic and formal logic, the study of valid inference, of truth values, of what must follow from what, is one of the deepest roots of discrete mathematics. Every time a computer evaluates a conditional statement, if this condition is true, do this. Otherwise, do that. It is running, in a very direct sense, on Aristotelian logical structure, 2,300 years old, and it's inside every if-then statement ever written. The second Greek contribution is more concretely mathematical, and it might be the single most striking example of ancient discrete mathematics, connecting directly to your life right now. His name is Euclid. He lived in Alexandria, Egypt, around 300 years before the Common Era, and he is famous for his Elements, that extraordinary 13-book synthesis of Greek mathematics. But within the Elements, almost buried among the geometric propositions, is a procedure I want to spend a moment on, because it's genuinely extraordinary. The procedure is for finding what we'd now call the greatest common divisor of two numbers, the largest number that divides evenly into both of them. If you have 48 and 18, the greatest common divisor is 6, because 6 goes into both and nothing bigger does. Euclid's procedure is simple but elegant. You take the larger number and subtract the smaller one. Then you take that result and subtract the smaller one again. if you still can, you keep subtracting until you can't anymore. And then you swap and repeat with the remainder. What makes this beautiful is that it always works. For any two positive integers, no matter how large, the process will always eventually terminate and give you the correct answer. Always, without exception. And here's the thing about Euclid's algorithm. It is over 2,300 years old, and your phone ran it this morning. Every time your device simplifies a fraction, every time a cryptographic system sets up a secure connection by working with large prime numbers, every time a piece of software reduces a ratio to its lowest terms, Euclid's algorithm, or a direct descendant of it, is running underneath. It is the oldest algorithm in continuous use by humanity, not the oldest idea, the oldest procedure, a step-by-step instruction for solving a problem that has been handed down unbroken for more than 2 millennia. Let that breathe for a second. Euclid is in Alexandria, surrounded by papyrus scrolls and the noise of the ancient world's greatest city, writing down a procedure, not because he imagines computers 23 centuries later, but because it's logically beautiful and solves a real problem. And it turns out that logical beauty and timeless utility have a way of being the same thing. So by the year 300 before the Common Era, across multiple continents and traditions, human beings have already laid down the first pillars of what we will eventually call discrete mathematics. They've counted in marks on bone. They've mapped the combinatorial landscape of rhythmic poetry and discovered binary numbers inside it. They've arranged integers in symmetric grids. They've formalized the structure of valid reasoning. And they've written down one of the oldest and most continuously useful algorithms in history. All of this without a name for what they were doing, without shared notation or vocabulary, just people playing with discrete structures because the problems were genuinely interesting. I find something enormously comforting in that. The impulse came first. The humans came first. The mathematics followed. But counting things and arranging them was only the beginning. Because once people started asking not just how many, but how many ways, that question opened a door that led somewhere nobody expected. So the question we ended with was this: not just how many, but how many ways. It seems small when you first hear it, like the difference between counting apples in a bowl and asking how many different arrangements of them are possible. One of those questions feels like arithmetic. The other one goes somewhere unexpected. For the mathematicians we are about to meet, that question became a kind of obsession, and they came at it from all over the world, centuries apart, through completely unrelated intellectual traditions. A linguist in 8th century Iraq, a mathematician in medieval India, a merchant's son in medieval Italy, and a French teenage prodigy who eventually decided, in a moment of spiritual crisis, to abandon mathematics entirely. What he left behind carries his name to this day. Let's begin in Basra. It's around 750 of the Common Era, and a scholar named Al-Khalil ibn Ahmad is sitting with a problem that has nothing to do with numbers. Al-Khalil was a linguist. one of the great ones. He essentially invented the formal study of Arabic prosody, the rhythmic patterns of Arabic poetry. He also compiled what may have been the first comprehensive Arabic dictionary, and that dictionary project is what made him, without quite meaning to, one of the earliest practitioners of combinatorics. Here's what Al-Khalil was trying to figure out. Arabic words are built on consonant roots, usually three consonants. Al-Khalil wanted to know how many possible words could exist in Arabic, how many distinct combinations of consonants could form a valid root. So he started counting, systematically and carefully, the way a mathematician would. How many ways can you pick three consonants from the 28 letters in the Arabic alphabet? How many ways can you arrange them once you have picked them? And here's what's wild about that project. He wasn't trying to do mathematics. He was trying to build a dictionary. A linguist in 8th century Basra invented cutting-edge discrete mathematics because he wanted to catalog every possible Arabic word. I find this pattern everywhere in the history of mathematics. The tools keep arriving from the wrong direction. People reach for them because they need them for something else entirely. And the mathematics turns out to be the interesting part of what they made. It keeps happening across every century and every continent we will visit tonight. Now let's travel roughly 4 centuries forward and most of the way around the world. It's around 1150 of the Common Era in what is now Karnataka in southern India, and a mathematician named Bhaskara II is writing a book, Bhaskara, sometimes called Bhaskaracharya, meaning Bhaskara, the teacher, was one of the great mathematicians of medieval India. The book that concerns us here is the one he called Lilavati. There is a legend attached to Lilavati, charming and probably apocryphal, that Bhaskara named it after his daughter. The story goes that he had carefully calculated the one auspicious hour for her marriage and set a water clock to measure it. But Lilavati leaned over the clock to peer inside, and a pearl from her necklace fell in and stopped the mechanism. The moment passed, and Bhaskara, to console her, promised that her name would live in a book studied for centuries. Whether any of that happened, the book is real. Among its pages, Bhaskara worked out problems involving permutations and combinations, how many ways a given number of objects can be arranged, how many selections of a given size can be drawn from a larger group. He had general methods for both. He was doing in 12th century India the same mathematics that Al-Khalil had been reaching toward in 8th century Basra. Different tradition, different century, different problem driving it, the same underlying structures. Let me take a moment here to explain what permutations and combinations actually mean, because the distinction is one of those things that sounds trickier than it is. Imagine you have 5 songs and you want to make a playlist of 3. If the order matters, if song 1, song 3, song 5 feels different from song 5, song 3, song 1, then you are counting permutations. Every different ordering is a different outcome. If the order doesn't matter and you just want to know which 3 songs make the cut, regardless of sequence, then you are counting combinations. Same 5 songs, same 3 chosen, but combinations ignores order and permutations tracks it. That's the whole distinction. And the numbers come out very differently. With 5 songs choosing 3 in order, you have 60 possible playlists. Choosing 3 where order doesn't matter gives you only 10 possible groups. The difference is a factor of 6, because each combination of 3 songs corresponds to exactly 6 different orderings of those same 3 songs. I think what this analogy is really doing is separating two things. Our intuition tends to blur the question of which things are selected versus how those things are arranged. Once you hold that distinction clearly, a lot of mathematics that used to seem obscure starts making sense. Which brings us to Leonardo of Pisa, known to history as Fibonacci. He was born around 1170 inches Pisa, traveled widely through North Africa and the Middle East because his father was a customs official in what is now Algeria, and somewhere in his travels he encountered the Hindu-Arabic number system, the one we use today, with its 10 digits and the crucial invention of 0 as a positional placeholder. In 1202, he published Liber Abaci, meaning the book of calculation, essentially an argument for why this number system was more powerful than Roman numerals for practical arithmetic, and a showcase of the kinds of problems it could solve. Buried in the middle of the book, almost as an illustration, was a puzzle about rabbits. Suppose you have a pair of newborn rabbits. They take a month to mature and then produce one new pair of offspring each month. How many pairs will you have after 12 months? The answer unfolds as a sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the 2 before it. Fibonacci almost certainly didn't originate this sequence. It appears in Indian mathematics centuries earlier, in work on the enumeration of poetic rhythms, which brings us full circle back to Al-Khalil's study of Arabic prosody. I genuinely love that connection. A sequence born from counting rhythmic syllables in classical Indian poetry shows up as a rabbit puzzle in a medieval Italian arithmetic textbook, and both trace back to the same mathematical territory. And here's the part that keeps surprising me. That sequence refuses to stay in textbooks. The number of spirals in a sunflower head, counted clockwise, is almost always a Fibonacci number. So is the number of spirals counterclockwise, the leaf arrangements of many plants, the branching patterns of certain trees. The ratio between consecutive terms in the sequence converges as you go further out toward approximately 1.618, the golden ratio, which architects and artists have been fascinated by for thousands of years. Why does a pattern derived from counting rabbits appear in biological growth structures? The answer involves the mathematics of efficient packing and optimal spacing, but it also gives you the faint feeling that somebody left this sequence in the world on purpose. Now let's talk about a triangle. Pascal's triangle is constructed almost absurdly simply. You start with a 1 at the top, below it, 2 ones, side by side. Each new row gets a 1 at each end, and each interior number is the sum of the two numbers directly above it. The rows go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Keep going as long as you like. I genuinely love this object. It looks so modest. Rows of numbers in a triangular arrangement. But the more you look at it, the more you realize it's like a cheat sheet the universe left lying around, encoded with more information than anyone told you about. The numbers in each row are precisely the combination values for that row's position, the answers to how many ways you can choose items from a group. Row sums are always a power of 2. Diagonal sums trace out the Fibonacci sequence. Each number encodes the coefficient you need when expanding a binomial to some power. Finding a new pattern hidden in the triangle is a rite of passage for mathematics students, and the patterns keep turning up. Worth noting, the triangle was not invented by Pascal. It appears in Indian mathematics from the 10th century, in the work of the Persian mathematician Al-Karaji around 1000 of the Common Era, and in the Chinese mathematician Yang Hui's writings in 1261. Pascal wrote a comprehensive treatise on it in 1654 that synthesized the known properties and extended them. The name attached itself, as European mathematical history was long in the habit of assigning European names to ideas that had been flourishing elsewhere for generations. But to talk about Pascal's triangle, you must talk about Blaise Pascal himself, and this is the story I keep coming back to. Pascal was born in 1623 inches, Clermont-Ferrand, France. He was one of those children who make everyone around them quietly uncomfortable, because the gap between his abilities and theirs was impossible to ignore. His father educated him personally and, worried the boy would become entirely consumed by geometry, deliberately withheld it from him. So young Blaise apparently deduced several of Euclid's theorems independently as a 12-year-old, working them out from scratch before being told formal geometry existed as a field. By 16, he had written a treatise on conic sections, the mathematical study of curves produced by slicing a cone at different angles, that working mathematicians of the era considered a genuine contribution. At 18, he designed and built one of the first mechanical calculators in history, a device of gears and wheels that could add and subtract, built to help his father manage tax accounts. He constructed around 50 working prototypes before arriving at a version he was satisfied with. He was 18. Then, in 1654, Pascal was in a carriage crossing a bridge near Paris. The horses, spooked, 2 of them plunged off the bridge into the water below. The carriage hung at the edge for a moment before the harness snapped and pulled it back. Pascal was physically unharmed, and yet something in him was permanently changed by that edge, by the gap between the carriage wheel and nothing beneath it. A few weeks later, on the night of November 23rd, 1654, he had an experience he described as 2 hours of fire. He wrote about it on a small piece of paper historians call the memorial. He apparently kept this paper sewn into the lining of his coat for the rest of his life, moving it from coat to coat as each one wore out. In it he wrote, God of Abraham, God of Isaac, God of Jacob, not of philosophers and scholars, certainty, certainty, feeling, joy, peace. He had arrived somewhere that mathematics could not reach, and he decided, largely, to leave mathematics behind. Let that sit for a moment. This was a person who had contributed to geometry at 16, built a calculating machine at 18, and in the very year of this experience was in active correspondence with one of the greatest mathematicians in France about the foundations of probability. He chose to walk away. He spent his remaining 8 years writing religious and philosophical works, including the scattered notes published after his death as the Pensées, which means thoughts, and which remains a significant work in the history of Christian philosophy. The bittersweet irony, the part that stays with me, is that his mathematical legacy didn't need him. The triangle already had his name. The probability framework was already in motion. He left the mathematics, and the mathematics kept carrying his name forward through every combinatorics textbook, every statistics course, every algorithm that uses binomial coefficients. The mathematician departed, the mathematics stayed, and those months of 1654 before the mystical experience ended his mathematical life included a correspondence with Pierre de Fermat that reshaped the direction of mathematics entirely. Fermat was born in 1601 inches, the south of France, and was, by official designation, a lawyer, a parliamentary councillor in Toulouse. He did mathematics as a private passion, communicated his discoveries mostly through letters, and had a habit of announcing results without supplying proofs, which made him simultaneously admired and quietly maddening to correspond with. This guy essentially invented modern number theory in the margins of his spare time. But the 1654 exchange with Pascal is different. It is specific, grounded, and one of the most consequential letters in mathematical history. The problem they were working on is called the problem of points. Two players are in the middle of a game of chance and have to stop before anyone has won. One is ahead. How do you divide the stakes fairly based on where the game stands? This had been puzzling mathematicians and gamblers for well over a century. Pascal and Fermat worked it out by imagining all the ways the game could have continued, counting how many of those possible futures each player would have won, and dividing the stakes proportionally. To count correctly, you need combinations. You need precisely the tools that Al-Khalil and Bhaskara and the triangle had been assembling for centuries before them. What emerged from that correspondence was the framework for calculating probability from first principles, not just for gambling disputes, but for any situation where you can enumerate outcomes and count the favorable ones. That framework became probability theory, which became the foundation of statistics, actuarial science, and eventually machine learning. Every weather forecast, every clinical trial, every algorithm estimating how likely you are to enjoy a film carries an unbroken line of reasoning back to two French mathematicians arguing by letter about an unfinished card game in 1654, one of whom would walk away from mathematics later that same year. There is something quietly satisfying about where we have arrived. We set out following the question of how many ways, and we have watched it gather momentum across 9 centuries and 4 continents. Al-Khalil counting consonant arrangements in 8th century Basra to build a dictionary. Bhaskara writing problems for his daughter in medieval India. Fibonacci carrying a new number system across the Mediterranean with a famous sequence hiding inside a rabbit puzzle. And Pascal, brilliant and restless, assembling the theory of arrangements and probability before setting it all down. From all of that, a set of tools quietly assembled itself. Permutations and combinations, the triangle with its improbable cargo of encoded patterns, the binomial theorem, the first principles of discrete probability. The building blocks are in place now, and they feel, once you have held them, genuinely intuitive rather than intimidating. Pascal's triangle, Fibonacci's sequence, the binomial theorem. All of these are about counting arrangements of things that are separate, distinct, countable. But what happens when you stop counting the things themselves and start counting the connections between them? What happens when the question isn't how many arrangements, but how are things connected? That question wouldn't be asked properly for another 100 years. And when it started with a walk across some bridges. Picture the city of Königsberg in the year 1735. It's a port city on the Baltic coast of what is now Russia, though back then it was part of the Kingdom of Prussia. The city sits astride the Pregel River, and the river splits around 2 islands before rejoining on the other side. And over the centuries, the people of Königsberg had built 7 bridges connecting these islands to each other and to the 2 banks of the river. 7 bridges spread across a beautiful, complicated tangle of water and land. Now here's the game the locals played. Could you take a walk through the city, crossing each of the 7 bridges exactly once, not skipping any, not crossing the same one twice, just a clean, complete tour, all 7 bridges, each visited exactly once. People had been trying this for decades. Nobody could do it, but nobody could prove it was impossible either. It was just one of those things, a puzzle that lived in the city, the way a rumor lives in a small town. And then someone brought it to Leonhard Euler. Euler was 28 years old in 1735 and already one of the most formidable mathematicians in Europe. He'd been born in Basel, Switzerland in 1707, the son of a pastor who had enough mathematical training to recognize that his son was something unusual. Euler ended up at St. Petersburg, working for the Russian Academy of Sciences, and he was prodigiously productive in a way that is almost hard to describe. Over his lifetime, he produced so much mathematics that his collected works run to more than 90 volumes. 90. And here's the detail that stops me every time I revisit this. He did a significant portion of this work while going progressively blind. He lost the sight in one eye in his late 20s from overwork, and lost most of the remaining vision in his other eye decades later. His response to total blindness was essentially to keep going, because He had trained himself to do most of the mathematics in his head. That's the person who looked at the Königsberg Bridge puzzle, and what he did with it was genuinely radical. He didn't try to find a route. He didn't trace paths through the city on paper, testing combinations. He looked at the problem for a while and said, essentially, the actual city doesn't matter. The distances between the bridges don't matter. The shape of the islands, the architecture, the river, the cobblestones, the whole beautiful mess of Königsberg. None of it is relevant to the question being asked. What matters is only this: which pieces of land are connected to which other pieces of land, and by how many bridges. So he threw everything else away. He replaced the landmasses with dots, 4 of them, representing the 2 islands and the 2 banks, and replaced the bridges with lines connecting the dots. 7 lines, 4 dots. That's all that was left of Königsberg. A tiny, almost laughably simple diagram. And then he solved the problem in a few lines of reasoning. Here's the key insight. And it's one of those things where once you see it, you can't unsee it. Euler noticed that if you can walk across all the bridges exactly once, then every time you enter a piece of land through one bridge, you must be able to leave through a different bridge, arrive on one bridge, depart on another, arrive, depart, arrive, depart, which means the number of bridges touching any given landmass must be even, because every entrance needs a matching exit, except possibly for the very first place you start and the very last place you end. So the rule is, in any map where this kind of walk is possible, at most 2 landmasses can have an odd number of bridges. In Königsberg, all 4 landmasses have odd numbers of bridges, not 2, all 4. The walk was impossible. It had always been impossible. Every person who ever tried it in the streets of that city was attempting something that the structure of the connections made impossible before they'd taken a single step. There's something quietly mischievous about that. The city looked like a puzzle. It felt solvable. People worked at it for decades, and the whole time, the answer was a calm, absolute no, encoded not in any detail of the city, but in the abstract shape of its connections. But what I find even more striking than the answer is the method. Euler looked at the real city with texture and history and people and performed an act of ruthless abstraction. He asked, what is the minimum information I need to answer this question? And everything else he discarded. What was left wasn't Königsberg anymore. It was something cleaner and more general, a network, a graph. Now, in mathematics, a graph isn't a chart with axes and plotted data. It's something different and in some ways simpler. A graph is just a collection of dots, where each dot represents something and lines connecting the dots, where each line represents a relationship between 2 things. That's it. 2 ingredients, dots and lines. Think about your own social world. You're a dot. Your friends are dots. Every friendship is a line. And suddenly, questions that feel fuzzy become precise. Are any of my friends also friends with each other? How many steps does it take to connect me to any stranger on earth. Which person in this network, if they disappeared, would break the most connections? These are graph theory questions, and they have exact mathematical answers. The internet is a graph. Web pages are dots. Hyperlinks are lines. Every time you click a link, you're traversing an edge in a graph containing hundreds of billions of nodes. The algorithm that decides which search results you see first is fundamentally a calculation about the structure of that graph, which pages have the most connections pointing at them, and which of those pages are themselves highly connected. Disease spread through populations is a graph problem. Airline routing is a graph problem. The way your GPS finds the fastest path through a city is a graph problem. All of it traces back to a man in 1735 who threw away a Prussian city and kept only the dots and lines. There's a genuinely jaw-dropping gap between how small that move was and how enormous its consequences became. Euler reportedly dashed off the paper fairly quickly because he didn't even think it was proper mathematics, too easy, too informal, nothing like the algebraic machinery he normally worked with. He called it a problem of geometry, of position, a question about arrangement rather than measurement. He was almost apologetic about including it. And yet here we are. Now, once you have the language of graphs, you start seeing graph-shaped questions everywhere. And some of those questions turn out to be surprisingly hard in ways that are almost philosophically interesting. One of the most famous is a problem so simple you could explain it to a child, and so stubborn it resisted professional mathematicians for over 100 years. In 1852, a young man named Francis Guthrie was sitting at a desk coloring a map of England, trying to fill in the counties so that no two neighboring counties were the same color. Guthrie was 21 years old at the time, studying both botany and mathematics, and he would later become a professor in South Africa, where he spent most of his career. But on this particular afternoon, he noticed something. No matter how complicated the map, it seemed like 4 colors were always enough. Not 5, not 6, 4. He mentioned this to his brother Zmida, who mentioned it to the mathematician Augustus de Morgan. And from there, the question spread through the mathematical world like a slow burning curiosity. Could you prove that any map, no matter how complex, could always be colored with just 4 colors? Or was there some particularly nasty map hiding out there that needed 5? Nobody could do either. Nobody could prove 4 was always sufficient. And nobody could construct a counterexample requiring 5. The 4-color problem became one of those haunting fixtures of mathematics, a question that looked embarrassingly simple and refused to yield. In 1879, a lawyer turned mathematician named Alfred Kempe published what he claimed was a complete proof for 11 years. The community accepted it. Then, in 1890, Percy Hewood found a fundamental error at the heart of Kempe's argument. Back to square one, the problem sat open for another 86 years. And here's the pivot moment, the one that still quietly unsettles people in the field. The 4-color theorem was finally proved in 1976 by Kenneth Appel and Wolfgang Haken at the University of Illinois. 4 colors are always sufficient. Done, but they use a computer to check 1,936 special cases. No human being has ever verified the proof by hand. No human being can. The chain of reasoning is too long, too atomized into computer-checked cases, to be held in a single mind. And that raised a question mathematics is still wrestling with. If a proof is technically correct, but no human being can understand it, is it really a proof? What is a proof for? A tool for establishing truth, in which case computer verification is fine, or a vehicle for understanding, in which case a proof that no one can follow has missed the entire point. The answer is there. The understanding is not quite. Let's move to another famous graph problem. And this one has a different flavor, not unresolved by philosophy, but unresolved by sheer computational difficulty. Imagine you're a traveling salesman. You have a list of cities to visit, each exactly once, and then you need to return home. Simple question, what's the shortest route? If you have 10 cities, there are only a few 100,000 possible routes. A computer handles that in a blink. If you have 20 cities, the number of possible routes is roughly 2 quintillion. That's 2 followed by 18 zeros. At 100 cities, the number of routes exceeds the number of atoms in the observable universe. Trying every route is not a practical strategy. The traveling salesman problem is the poster child for a family of problems called NP-hard, a technical term meaning, roughly, that checking a proposed solution is easy, but finding the best solution seems to require time that explodes exponentially as the problem grows. No one has proven these problems can't be solved efficiently, but no one has found an efficient way to solve them. The question of whether they can be is, in fact, one of the great unsolved problems in mathematics with $1 million prize attached to it. Simple to state, monstrous to solve. Now, within the language of graph theory, mathematicians have built a whole vocabulary for the shapes networks can take. A tree is a graph with no loops, or family. Trees are literally trees in this sense, which is why we call them that. So are folder hierarchies on a computer, org charts, the branching structures of language. Cycles are graphs with loops, and most real-world networks roads, the internet, the human circulatory system are full of them, and complete graphs where every node connects to every other node turn out to be important for a beautiful reason. I want to briefly mention it has to do with someone named Frank Ramsey. Ramsey was a philosopher and mathematician at Cambridge in the late 1920s, and he was the kind of person whose talent left everyone around him slightly breathless. He was a close friend of Ludwig Wittgenstein, on intimate intellectual terms with John Maynard Keynes, and he had translated the Tractatus Logico-Philosophicus from German to English when he was 19 years old. Nineten. He died in 1930 from a liver operation, aged 26, and mathematics is still unpacking ideas he barely had time to sketch out. One of the things that grew from his work is this: in any sufficiently large structure, order is unavoidable. Here's a concrete version. Imagine a party with 6 people. Some pairs know each other, some are strangers. Arrange the friendships however you like. Make it as random as possible. Ramsey's theory guarantees that no matter what you do, you will find either three mutual friends or three mutual strangers somewhere in that group. You cannot escape both. The structure is too small to hide from order. Scale this up and the principle deepens. In a large enough network, surprisingly, regular patterns will always emerge, no matter how randomly the connections were made. Complete disorder at sufficient scale is mathematically impossible, and something about that idea stays with me. It's almost like a promise embedded in the mathematics. Chaos has limits. In any large enough collection of connections, meaning insists on emerging. So let's take stock of where we've arrived by following Euler across those 7 bridges. We started with a local puzzle: can you walk a certain path through a city? And somewhere in the act of answering it, a new branch of mathematics was born. A language for connections, for relationships, for the hidden structure of how things relate to other things. 3 centuries later, that language is the invisible scaffolding of the internet. It's how epidemiologists trace a virus through a population. It's how logistics companies route packages across continents. It's the foundation of every social network on Earth. A walk that no one in Königsberg could take in 1735 became, over 300 years, the backbone of the modern world. How did that happen? The answer, I think, is that Euler did something that looks small, but is one of the deepest moves in all of mathematics. He stopped looking at the things and started looking at the connections between them. He threw away the content and kept only the structure. And it turns out the structure is where almost everything interesting lives. But here's a thought to carry into sleep. Around the same time that Euler was learning to see the world as dots and lines, another kind of stripping down was quietly beginning somewhere else, not of cities, but of thought itself. What if you could do to logic what Euler did to Königsberg? What if you could throw away the content of an argument, the actual meaning of the words, and keep only the structure of the reasoning? What if true and false were just 1 and 0? That question wouldn't be answered for another century. But when it started with a man trying to turn the very process of thinking into something you could write down like an equation. And what he built from that strange ambition is a thread that runs directly into the machine you might be listening to this on. From the structure of connections to the structure of thought, that's where we're going next. So let's start with a dream, because this whole story begins with someone who dreamed far too big. Gottfried Wilhelm Leibniz was born in Leipzig, Germany, in 1646. And he was the kind of person who made everyone around him feel slightly inadequate. He was a philosopher, a mathematician, a diplomat, a librarian, a legal theorist, and somewhere in between all of that, a man obsessed with a single idea he could never quite finish. The idea was this: what if argument itself could be formalized? What if, instead of debating whether something was true or false, you could simply calculate it? What if you could build a kind of universal language of thought, an alphabet of concepts, so precise and complete that any disagreement about philosophy, about physics, about justice could be settled by sitting down and computing the answer. He called it the characteristica universalis, a universal characteristic. And honestly, I find this idea almost unbearably ambitious. Not foolish, unbearably ambitious. Because what Leibniz was saying is that human reason itself has a structure, and that structure could be written down. He spent years on it and never finished. But along the way, around 1679, he sketched something else, a number system that used only two symbols, a 1 and a 0. He wrote privately that this binary arithmetic, as he called it, had a kind of mystical elegance, that all of creation could be expressed as combinations of something and nothing, 1 and 0. He even sent it to the Emperor of China because he thought it might help explain Christian theology to Confucian philosophers, which is a sentence that only makes sense when you understand just how strange and sprawling Leibniz's mind was. He was, by any reasonable estimate, about 300 years too early. Now, the dream of a formal logic, a mathematics of reasoning, sat more or less dormant for nearly 2 centuries, not entirely forgotten, but waiting for the right person to pick it up and do something completely unexpected with it. That person was born in Lincoln, England, in 1815, to a man who made shoes. George Boole's father was a cobbler, not a wealthy one, not a man who could afford tutors or universities or the kind of education that was in early 19th century England, the exclusive property of people with money. What his father could afford was the public library, a handful of books, and an apparently inexhaustible curiosity. George Boole taught himself. He taught himself Latin, then Greek, then French, then German, so he could read the mathematical journals directly. He taught himself advanced mathematics out of library copies of works by Laplace and Lagrange, books that most people encountered only at Cambridge and only after years of formal preparation. He never attended university, not once, and yet by the time he was in his 20s, he was corresponding with some of the leading mathematicians in Britain as a near equal, and by his early 30s, he was a professor of mathematics at Queen's College in Cork, Ireland, which, if you think about the class system of Victorian England, is the kind of thing that makes you stop and sit with it for a moment. This was not how that world worked. You needed the right school, the right connections, the right family. Bull had none of those things. He had the library. In 1854, when he was 39 years old, he published a book called An Investigation of the Laws of Thought. And what he did in that book is something that still strikes me as one of the cleanest intellectual moves in the entire history of mathematics. He took logic, the ancient study of how arguments work, how we reason from premises to conclusions, and he showed that it was algebra, not like algebra, not analogous to algebra. It was algebra running on a different set of values. Let me give you the everyday version first, because it's one you already know by heart even if you've never heard the word Boolean. Every single time you type something into a search bar and add quotes or a minus sign to filter your results, you're writing Boole's notation. If you search for, say, cats and funny, not dogs, you're doing Boolean algebra. The AND means you want results that satisfy both conditions at once. The NOT means you're excluding something. And if you searched for cats or kittens, you'd get results that satisfy either one and or not three operations. That's the whole system. And here's what's beautiful and slightly staggering about it. Boole showed that any logical statement, any chain of reasoning that involves combining truth values can be broken down into combinations of just those three operations. It doesn't matter how complicated the argument is, and or not every argument ever made that can be formalized reduces at its foundation to those three things. He also showed that these operations followed algebraic laws. You could manipulate logical expressions the way you manipulate algebraic ones. There were equivalences, transformation, simplification, logic. It turned out had an algebra. Now here's a person worth knowing alongside Boole, because they worked in related territory at almost exactly the same time. Augustus de Morgan was a British mathematician, born in India in 1806, who spent most of his working life in London and who had a gift for clarifying things that other people found murky. De Morgan and Boole were friends and correspondents, and De Morgan arrived at some results that any programmer today uses constantly, usually without knowing whose name is on them. De Morgan's laws. They sound technical, but they're completely intuitive once you see them. The first one says that not the combination of A and B is the same as not A or not B. The second says that not the combination of A or B is the same as not A and not B. In plain English, if something is not both a cat and funny, that means it's either not a cat or not funny or both. These laws let you flip between and or when you're negating things, which turns out to be enormously useful when you're designing logical systems. Every programmer who has ever debugged a conditional statement has, in some small way, invoked De Morgan. Let's shift gears slightly, because around the same era, a different mathematician was formalizing something that would eventually connect to all of this in a surprising way. Georg Cantor was born in St. Petersburg in 1845 and spent most of his career in Germany, where he created something that his contemporaries found deeply unsettling and that we now call set theory. A set, in Cantor's sense, is simply a collection of things, the set of all even numbers, the set of all cats in London, the set of all solutions to some equation. It sounds almost too simple to be interesting, but what Cantor did with this simple idea was remarkable. He started asking questions about the sizes of infinite sets, and in doing so, he discovered that infinity is not one thing. There are different sizes of infinity. Some infinities are bigger than others, which is, even now, a thought that takes a few passes to really absorb. You've almost certainly seen one of his tools without knowing it. The Venn diagram, those overlapping circles you drew in school to compare things, is essentially a visual representation of Boolean algebra done in terms of sets. The overlapping region where the circles intersect is the AND. The combined region of both circles is the OR. Everything outside a circle is the NOT. Set theory and Boolean logic are, at a deep level, two different visual languages describing the same underlying structure. Cantor gave us the geometric picture that let us see the logic spatially. And now here's where the story hits a wall, a very elegant wall. Around the turn of the 20th century, mathematicians had grown ambitious. Boole had shown that logic was algebraic. Cantor had built a general theory of collections. Peano had formalized the natural numbers from first principles. There was a feeling that maybe, just maybe, mathematics itself could be placed on a single solid logical foundation, that you could take a small number of axioms, basic assumptions so obvious they couldn't be doubted, and derive all of mathematics from them as logical consequences. Leibniz's old dream, but now with the actual tools to attempt it. Bertrand Russell, who was 28 years old in 1900, the year the project was really catching fire, was one of the people who believed this most deeply. He was a British philosopher and mathematician, born into the aristocracy in 1872, deeply brilliant, and, as would become apparent, more than a little fond of pointing out when other people were wrong. In 1901, he found something, a small crack in the foundation of Cantor's set theory, not a philosophical objection, an actual logical contradiction. And it went like this. If sets are just collections of things, can a set be a member of itself? Most sets aren't. The set of all cats is not itself a cat, so it's not a member of itself. But you could imagine a set of all things that are not cats, which would include itself. So some sets contain themselves and some don't. Fine. Now consider the set of all sets that don't contain themselves. Does it contain itself? If it does contain itself, then by definition it shouldn't, because it only contains sets that don't contain themselves. But if it doesn't contain itself, then by definition it should, because it's supposed to contain everything that doesn't contain itself. And it doesn't contain itself. So it contains itself if and only if it doesn't contain itself. The analogy Russell himself later offered, and which is sharper in some ways, is the barber who shaves everyone in town who does not shave themselves. Does the barber shave himself? If he does, he shouldn't. If he doesn't, he should. There is no consistent answer. The logic loops and breaks. Russell's paradox, as it became known, was the kind of discovery that sends a chill through a whole field. It meant that naive set theory, the version Cantor had built and everyone had been using, was inconsistent. If you followed the rules all the way down, you arrived at a contradiction, And a mathematical system that contains a contradiction is useless, because from a contradiction you can prove absolutely anything. The whole foundation was cracked. The response was dramatic. Russell and Alfred North Whitehead spent a decade writing the Principia Mathematica, a 3-volume work that attempted to rederive all of mathematics from scratch, using a very carefully controlled version of set theory with rules specifically designed to avoid paradoxes. It is famously one of the least readable books ever written. There is a running joke that it takes hundreds of pages before the book gets around to proving that 1 plus 1 equals 2. All of this was setting a stage, though nobody in 1901 or 1910 or even 1930 quite knew what stage it was, because the project of formalizing logic raised a question that nobody had seriously confronted before. Not just can mathematics be built from logical axioms, but what exactly can formal systems do? Is there a limit to what logical rules can derive? Can every true mathematical statement be proved? Is there a systematic procedure that could, in principle, settle any mathematical question if you just followed the steps long enough? These questions were floating in the intellectual air through the 1920s and into the 1930s, and the answers, when they came, were so strange and so definitive that they changed not just mathematics, but the way we think about the limits of knowledge itself. But let me tell you about the part that stops me every time I come back to this story. The part about the connection that nobody saw coming, because the person who saw it wasn't a philosopher or a logician. He was a 21-year-old graduate student. Claude Shannon was born in Michigan in 1916 and arrived at MIT in the mid-1930s to study mathematics and electrical engineering. He was bright and curious, and apparently not the most conventional of students. And in 1937, while working on his master's thesis, he noticed something. He was thinking about electrical switching circuits made of switches, each of which is either open or closed, off or on, and he noticed that the behavior of these circuits followed rules. The rules for combining switches in series, where current only flows if both switches are closed, looked exactly like the AND operation. The rules for combining switches in parallel, where current flows if either switch is closed, looked exactly like OR, and the rule for a switch that blocks current when another is open looked exactly like NOT. George Boole's 83-year-old Algebra of Logic, which had been sitting on library shelves since 1854, considered an interesting philosophical curiosity with no obvious practical application, was the exact mathematics needed to design electrical switching circuits. Every possible circuit configuration could be expressed as a Boolean expression. Every Boolean expression could be built as a circuit. The language of logic and the language of hardware were the same language. Shannon proved this in his master's thesis. He was 21 years old. And that's not even the interesting part. The interesting part is that once you can design circuits using Boolean algebra, you can build circuits that compute, circuits that take inputs, apply and gates, or gates, not gates, and produce outputs, circuits that perform logical operations at the speed of electricity, circuits that can, in principle, carry out any logical procedure that can be stated formally. Shannon was 21 years old, sitting at MIT, and in noticing the connection between an old philosophical algebra and a new electrical technology, he had just sketched the theoretical skeleton of the digital computer. And here's the part that carries a quiet weight I can't quite shake. George Boole died in 1864. He was 49 years old. He had walked to work in heavy rain, arrived soaking wet, lectured anyway, never properly recovered, and was gone within weeks from pneumonia. He died thinking that his work on the laws of thought was, at best, a minor contribution to philosophy, a curiosity, a neat idea about the relationship between logic and algebra that might interest specialists but would never change anything large. He had never seen a light bulb. The first practical incandescent bulb was demonstrated by Edison 15 years after Boole died. The first electronic computers came 80 years after he was gone. The transistor, which is a solid-state switching device, a physical embodiment of the Boolean logic he wrote down in a library in Lincoln, wasn't invented until 1947. And the integrated circuit, the chip, the processor, every piece of digital hardware that has ever existed or will ever exist traces its fundamental logical structure back to the operations Boole described on a page in 1854. Every AND gate, every OR gate, every NOT gate in every device in the world tonight. All of it, Boole's algebra. He died thinking he had built a philosophical footnote. He had built the foundation of the information age. Let that rest for a moment. Boole gave us the logic. Shannon showed it could be wired into circuits, but there was still a question floating in the air that nobody had answered cleanly. And, in a way, nobody had even asked it precisely enough to answer. What exactly can a machine compute? Is there a limit? Are there problems that are simply beyond any formal procedure, no matter how long it runs, no matter how powerful the hardware? And if there is such a limit, how do you even define it? How do you prove a boundary around the very idea of computation? That question would be answered by a man sitting in a Cambridge meadow in 1936, imagining an impossible machine that had no moving parts, no electricity, no physical form at all, a machine made entirely of logic. From formal logic to formal computation, from the question of how we reason to the question of what a machine can do, that thread running from Leibniz's dream through Boole's library, through Shannon's circuits, leads directly to the idea of computation itself, and to the man who defined what a computer is before a single programmable one had ever been built. His name was Alan Turing. He was 23 years old in 1935, a graduate student at King's College in Cambridge, and he was about to answer a question that the mathematician David Hilbert had posed to the entire mathematical world 7 years earlier. Hilbert had asked, essentially, is there a mechanical procedure, a finite series of steps, that can decide whether any mathematical statement is true or false? He called it the Entscheidungsproblem, the decision problem, and he asked it with the optimism of someone who fully expected the answer to be yes. Turing said no. But to prove no, he first had to define what a procedure even was. And the definition he came up with is one of those things that the first time you really understand it feels almost too simple to be serious. Imagine someone sitting at a long table with an infinitely long strip of tape stretched out in front of them. The tape is divided into squares. Each square either has a symbol on it or is blank. Let's say just two symbols, a 0 or a 1. The person can read the square in front of them, erase it, and write something new. Shift one square left or one square right, and consult a rule book, a finite list of instructions that tells them what to do based on what they just read. That is the entire machine. No electricity, no gears, no screen, just a tape, a pendule, an eraser, and a rule book. Turing called this a computing machine. We now call it a Turing machine. And here's the thing that genuinely stopped me when I first understood it properly. This absurdly simple imaginary device turns out to be exactly as powerful in a formal sense as any computer that has ever been built. If a problem can be solved by any computer anywhere, your phone, a supercomputer, a machine the size of a warehouse, it can, in principle, be solved by the tape and rulebook version. We have made computers faster, quieter, smaller, incomprehensibly more sophisticated. We have not made them more capable in the mathematical sense Turing defined capability. The boundary he drew in 1936 still holds. And here's what's wilder still. Turing immediately used his new definition to prove that there are problems no Turing machine, and therefore no computer, can ever solve. Not hasn't solved yet, cannot solve, in principle, ever, regardless of how long it runs or how powerful it gets. The specific problem he proved impossible is called the halting problem. It sounds almost like a reasonable engineering question. Given a program and its input, can you determine in advance whether the program will eventually finish or run forever? Turing proved that no algorithm can answer this question in general. His proof is a knot tied so tight the rope disappears. He assumes you have some algorithm that can answer the halting question for any program, then constructs a new program whose behavior directly contradicts whatever your algorithm predicts. The contradiction is airtight. The algorithm can't exist. There is a word in mathematics for problems that no algorithm can solve. The word is undecidable. And the halting problem was the first problem ever proved undecidable. Turing had not just defined computation, he had mapped its outer limits and found that the territory has an edge. Let that sit for a moment. He drew the complete boundary of what any computer can ever do, using a thought experiment involving an imaginary tape, before a single general-purpose computer had been built. And then the war arrived. But 1939, Turing, now 27, was at Bletchley Park, a Victorian manor house in the English countryside, working alongside mathematicians and linguists and crossword champions whom the British government had quietly assembled. Their target was the Enigma machine, which the German military used to encrypt all its communications Enigma worked by routing each letter through a series of rotating mechanical wheels, the configuration shifting with every keystroke so that pressing the same key twice produced two completely different encrypted letters. The number of possible Enigma settings was something in the neighborhood of 150 quintillion. Brute force was simply not an option. Picture those huts at Bletchley, intercepted messages arriving as pure gibberish, cold tea going stale on the table, the settings resetting every night at midnight, the clock already running again. Turing's approach was to find mathematical leverage, structural patterns that the Germans introduced unwittingly through human laziness and procedural habits. Weather reports ended in predictable phrases. Operators reused lazy settings. Structure in apparent randomness is structure you can exploit. Turing designed an electromechanical device called the bomb to rapidly eliminate impossible settings by hunting for those patterns. The intelligence produced at Bletchley, code named Ultra, is credited by historians with shortening the war by at least 2 years, saving millions of lives. Discrete mathematics, applied with urgency, changing history in real time. Turing did not survive the peace. In 1952, he was prosecuted by the British government for being gay. He was convicted, chemically castrated. He died in 1954 at the age of 41. The coroner ruled it suicide. I can't move through this cleanly. The person who defined what a computer is, who helped break the Nazi encryption system, was destroyed by the country he helped protect. The history of ideas is not always a comfortable history. Sometimes it is a record of what we owe and how badly we failed to pay it. Now, we need to talk about a different person, working at almost exactly the same time, who asked an entirely different question. Not what can a machine compute, but what is information? Actually, when you strip away every assumption and look at it as a mathematical object. His name was Claude Shannon. He was born in 1916 inches Petoskey, Michigan, grew up building things, telegraph lines strung to a friend's house half a mile away, radios, model planists. He ended up at MIT and then Bell Telephone Laboratories in New Jersey, which in the 1940s was probably the most productive research institution in the history of applied science. Colleagues remembered him riding a unicycle down the corridors while juggling. He also apparently built a flame-throwing trumpet. And then he sat down and wrote the most important paper in the history of communications. The paper was called A Mathematical Theory of Communication, published in 1948. The title undersells it so severely it's almost misleading. Before Shannon, nobody had a precise mathematical definition of information. You could transmit messages, store things, communicate ideas, but there was no formal way to measure how much information a message contained, how efficiently it could be encoded, what the hard limits of reliable transmission were. Engineers worked with rough intuitions. Shannon made them exact. Here's the core idea. Think of the game 20 questions. You're thinking of something, and I have to figure out what it is through yes or no questions only. Every good question cuts the space of possibilities roughly in half. Is it alive? Is it bigger than a bread box? Does it move? Each answer narrows the field. The minimum number of yes or no questions I would need to uniquely pin down the answer. That number, Shannon said, is the information content of the answer. And he named the unit. He called it the bit from binary digit. Think of a bit like a light switch, on or off, one or zero. And then Shannon showed with mathematics precise enough to build technology on that you can encode literally anything in bits, every word in every language, every photograph ever taken, every piece of music ever composed, your grandmother's voice on a phone call, everything, when you go far enough down, is a sequence of light switches. That is not a metaphor. That is literally what is happening inside every digital device on the planet right now. And then this is where the paper goes from important to astonishing. Shannon derived theorems about what you can and cannot do with information. He proved that every communication channel, copper wire, fiber optic, radio signal, satellite link, has a maximum rate at which information can be sent reliably, a hard ceiling. This ceiling depends on just two things, the bandwidth of the channel and the noise in it. And here is the theorem that changes everything. As long as you stay below this ceiling, you can always encode your message so that it arrives without error, no matter how noisy the channel. Before 1948, engineers thought of noise the way you think of rain, unavoidable, something you minimize and live with. Shannon said, noise is a constraint, not an enemy. Understand the mathematics of the constraint and you can communicate reliably within it. Not reduce the error, eliminate it. This is what I mean when I say information has physics. Shannon proved that information obeys precise mathematical laws governing how it can be stored, transmitted, and protected from corruption. Energy has physics. Mass has physics. Information has physics. And one person worked that out largely alone in 1948. The fields that came into existence in the years following Shannon's paper include data compression, error correction theory, digital communications, and the entire mathematical framework underlying every network ever built. Every time data moves from one place to another in the digital world, it does so under the governance of theorems. Shannon proved in 1948. One of his colleagues at Bell Labs immediately understood what the practical implications were. Richard Hamming was born in 1815, and he had a productive, almost professionally useful sense of irritation. In the late 1940s, Bell Labs had early electromechanical computers running overnight batch jobs. When a machine hit an error, it stopped and waited, sometimes for hours, for an operator to come in the next morning and restart the job. Hamming's response, reconstructed from his own later writings, was essentially, if the machine can detect that an error occurred, why can't it figure out where and fix it? He sat down and worked out how what he invented is called an error correcting code. When you transmit a message, you don't just send the message, You send the message, plus some extra bit, carefully derived from the original, that contain enough structural information that the receiver can identify not just that an error occurred, but exactly which bit went wrong and correct it automatically. Your phone does this continuously, invisibly. Every data packet crossing a wireless network, every bit pulled from flash memory, is protected by a descendant of Hamming's insight. When your music plays without interruption despite a momentary signal drop, that's Hamming codes working in the background, the way the best infrastructure always does, silently, reliably, without asking for credit. There's something I keep coming back to in this part of the story. Turing defines the limits of computation in 1936. Shannon measures the limits of information in 1948. Hamming shows how to protect information in transit in 1950. None of them was trying to build a technology. All of them were chasing clean mathematical questions. And between the three of them, within 15 years and a few hundred miles, they laid the complete theoretical foundation for the digital age. Before we leave this era, I want to tell you about someone who turned mathematics itself into something that looks, from a certain angle, like a living social network. His name was Paul Erdős. Born in Budapest in 1913, a prodigy who by the age of 4 could calculate in his head how many seconds a person had been alive. He got his doctorate in mathematics, accumulated a fellowship, accumulated another, and then, at some point, simply stopped having an address. He gave away nearly all his money. He owned almost nothing, just a single half-empty suitcase that accompanied him everywhere. He would telephone a colleague, announce that his brain was open, show up at their door, work with them intensely for days or weeks on whatever problem was in front of them, then move on to the next mathematician in the next city or country. He drank enormous quantities of strong coffee. He published around 1,500 mathematical papers over his lifetime, more than any mathematician in history except Euler. He had over 500 direct collaborators. And because of this, an idea emerged organically from the community, the Erdős number. If you co-authored a paper directly with Erdős, your number is 1. If you worked with someone who worked with Erdős, your number is 2. What became clear as mathematicians mapped these chains is that the collaboration network was extraordinarily tightly connected. The average Erdős number among research mathematicians is less than 5. Einstein's was 2. It's a playful idea. And mathematicians wear their numbers with fond self-deprecation. But it points at something real, graph theory, the abstract mathematics of connections and networks that Erdős himself worked on turned out to describe the mathematical community itself. The subject and its practitioners were shaped like each other. Now, here's something worth sitting with. Turing proved in 1936 that there are problems no computer can ever solve. Not because we haven't built a good enough machine, but because the problem is mathematically unsolvable by any step-by-step process, any machine, ever. And here we are, nearly a century later, and every computer ever built, from the first room-sized vacuum tube machines to the phone in your pocket, is still fundamentally a Turing machine. We've made them faster. We've made them smaller. We haven't made them more capable in the formal sense. The boundary Turing drew in 1936 with an imaginary tape and a rulebook still holds. And then Shannon showed 12 years later that information itself has a formal structure, that it obeys laws as rigorous as the laws governing energy or mass, that the bit is a real unit naming a real thing. Put these two ideas together and you feel the architecture beneath the architecture of everything digital. Every word arriving in your mind right now is information in Shannon's sense, measured in bits, bounded by channel capacity, protected by error-correcting codes. Every step of the process generating this sound is computation in Turing's sense, running on machines whose fundamental logical structure traces back to an imaginary tape from 1936. The entire digital world, your phone, the internet, streaming music, satellite navigation, electronic medicine, wireless communication, every technology shaping your waking hours is built on a foundation laid in roughly 15 years by a handful of people who were not engineering anything, just asking questions they found interesting. There is something about that which produces in me a kind of vertigo. These were not practical people solving practical problems. They were theorists chasing pure ideas for their own sake. And the ideas turned out to be load-bearing walls in a structure that now holds up civilization. Shannon gave us the theory of information. Turing gave us the theory of computation. Erdos connected mathematicians into a living network. But all of this, the bits, the algorithms, the graphs, the logic gates, was about to walk out of the university and into your pocket. And the way it got there involves a story about prime numbers, secret message, and a problem so hard that the security of the entire internet depends on nobody being able to solve it. So let's talk about prime numbers. You know prime numbers: 2, 3, 5, 7, 11, 13. Numbers with exactly 2 divisors, 1 and themselves. You probably learned about them in school and then wondered at some point when you'd ever use them again. The answer, it turns out, is right now. Every time you open your banking app, every time you log into your email, every time you send a message that you expect to be private, prime numbers are quietly doing something extraordinary on your behalf. Here's the story. It's 1977. 3 mathematicians at MIT, Ron Rives, Adi Shamir, and Leonard Edelman, are sitting with a problem that had seemed, for centuries, entirely theoretical. The problem goes like this. Multiplication is easy. Take 2 large prime numbers, multiply them together, and you get a product done in seconds. But here's the strange thing. If I give you that product, that result, and I don't tell you which 2 primes I used, figuring out what they were is genuinely, ferociously hard. It sounds like it should be simple. You have a number. It has two prime factors. Find them. But when the number has, say, 300 digits, the best mathematical techniques we have for factoring it, even running on the fastest computers in the world, would take longer than the current age of the universe. Not because of a shortcut we haven't found yet, because of something deep about how primes are distributed. The factoring problem is just hard. Revest, Shamir. And Adelman looked at this asymmetry. Multiplication, easy in one direction, practically impossible in reverse. And they saw a door. Let me give you the analogy that I think makes this click. Public key cryptography is like a mailbox on the street, the kind with a slot in the front. Anyone walking past can push a letter through the slot. The slot is public. Anyone can use it, but only the person who has the key can open the box and read what's inside. Your encryption key is the slot. You can publish it openly, share it with anyone, post it on a billboard if you want. Messages encrypted with it can only be decrypted by your private key. The key only you hold. The math underneath this, the reason it works, is those two large primes and the fact that deriving the private key from the public one would require factoring a number that no computer alive could crack before the sun burns out. Euclid, working in Alexandria around 300 BCE, proved that prime numbers are infinite in supply. He had no idea. He could not have had any idea. He was just following a proof about pure structure, with no application in mind, because pure structure was enough. And now his primes are the reason your credit card number is safe. Just let that sit for a second. Now, let's shift gears, because RSA is only one piece of the picture, and the other pieces are wild in a different way. Do you use Google? Of course you do. Do you know why Google search results appear in the order they do? Not because Google counts how many times a word appears on a page. That would be terrible. Spammers figured that out within hours of any such system going live. The reason Google was revolutionary when Larry Page and Sergey Brin launched it from Stanford in 1998 is that it asked a completely different question. Not does this page contain the word you searched for, but which pages do other pages trust? Page and Brin modeled the entire internet as a graph. Every web page is a node. Every hyperlink is an edge. And their insight, which became the PageRank algorithm, was that a page is important if important pages link to it. It's a recursive definition. You're trusted if trusted people trust you. The algorithm they use to solve this is, at its core, a walk through a graph, an imaginary random user clicking links repeatedly, landing on pages with probability proportional to how many links point to them. Settle that random walk to its steady state, and you have a ranking of the entire web. It is, in its mathematical bones, graph theory. And here's where this gets genuinely thrilling to me. The same mathematical object, a graph that Leonhard Euler sketched on a piece of paper in 1735 to solve a puzzle about bridges in Königsberg, is the object underlying PageRank. Euler's graphs route your internet traffic. Euler's graphs power your GPS navigation. Every time your phone finds the shortest path between two locations, it's running a shortest path algorithm on a graph where intersections are nodes and roads are edges. Euler's graphs model how diseases spread through populations. Epidemiologists map contact networks as graphs and trace infection paths through them. The same dots connected by lines object that Euler drew while thinking about a pleasant walking route in a city he'd never visited is in all of it. None of these are loose metaphors. They're literally the same mathematics applied to different kinds of bridges. I find something deeply satisfying about that. Euler was 48 years old, living in St. Petersburg, probably amused by the whole Königsberg puzzle. He solved it just by finding the right way to look at it, a way that made the solution obvious once you saw it. He had no particular destination in mind. He wasn't thinking about the internet. Obviously, he was thinking about an elegant problem and the mathematical object he left behind. The abstract notion that you can represent relationships between things as dots connected by lines is now one of the most shy and most structures in all of computing. The geometry of connections turned out to be fundamental, and algorithms, the step-by-step procedures that are discrete mathematics made practical, are running constantly in the background of your life in ways you probably don't notice. The recommendation engine that surfaced the show you watched last week, that's a form of discrete optimization, a system walking through a massive graph of users and content and finding connections that maximize the probability you'll keep watching. Spell check. Every time your phone corrects a typo is built on edit distance, a beautiful concept from graph theory that measures how many single character steps it takes to transform one word into another. The compression that makes photos and songs transmittable at all, that's built on Huffman coding, a tree-based algorithm from 1952 that assigns shorter bit sequences to more frequent patterns, shaving bytes off everything you send. Even the schedule that determines when your train departs and which track it uses is a solution to a combinatorial optimization problem that is, at its root, discrete math. Your life is being continuously managed by algorithms built from ideas we've been tracing all night. Boole's logic gates, Shannon's bits, graph theory, number theory, trees, binary sequences, all of it running in hardware you carry in your pocket without thinking about it. Now here's a cloud on the horizon, a fascinating one. In 1994, at Bell Labs in New Jersey, a mathematician named Peter Shor did something that sent a quiet chill through the entire cryptography community. Shor developed what's now called Shor's algorithm, a procedure designed to run on a hypothetical quantum computer that could factor large numbers efficiently, not in the age of the universe, in hours, possibly minutes. If a large enough quantum computer is ever built, and this is still a genuinely open question, Shor's algorithm would break RSA, the prime number lock that protects the internet would come undone. The asymmetry that Rivest, Shamir, and Adleman built their system around would cease to hold. This isn't a distant theoretical curiosity. Governments and tech companies are working on it right now. There's an entire field called post-quantum cryptography, the search for mathematical locks that remain hard to pick even for quantum computers. Some of them are also built on problems from discrete mathematics, just different ones. Problems involving lattices and error-correcting codes rather than primes. The arms race is ongoing, and discrete math is on both sides of it. And what I think is beautiful about that is this: the problem of how to keep secrets, how to communicate privately, how to establish trust at a distance. This is maybe the oldest problem in all of human organization. Ancient generals encoded messages, medieval scholars built ciphers, and the latest chapter of this story is playing out in quantum physics labs and cryptography conferences, still built on the same ancient idea of finding something that's easy in one direction and hard in the other. The problems got bigger, the stakes got higher, the shape of the question is the same. Now, let's pull all the threads together, because this is the moment I've been building toward. And here's where all the threads come together. The primes that Euclid studied in 300 BCE are protecting your credit card right now. The graphs that Euler drew in 1735 are routing your internet traffic. The Boolean logic that Boole invented in 1854 is running in every chip in your house. The bits that Shannon defined in 1948 are carrying your voice across the planet. None of these people knew each other. Most of them lived centuries apart, but they were all working on the same thing: the mathematics of things that come in pieces, discrete math, not smooth, not flowing, not the calculus of curves and continuous change, the mathematics of steps, of choices, of separate, countable, distinct things, on or off, true or false, connected or not, this prime or that one. And here's the revelation I want you to carry into sleep with you tonight. We think we live in a continuous world, smooth, flowing. When you reach out and touch something, it feels like your fingers travel through perfectly seamless space. When you watch a sunset, the colors seem to blend without interruption, orange fading into violet without a single seam. When you hear music, the sound seems to roll in an unbroken wave. But zoom in on your screen right now, far enough, and it dissolves into pixels, tiny, discrete squares of color, each one a separate value, each one a distinct number stored somewhere in memory. The smooth image you see is an illusion built from pieces so small and numerous that your visual system fills in the gaps and mistakes the mosaic for a painting. Your phone camera doesn't capture reality. It samples reality at a rate high enough that you can't tell the difference. Your music isn't a continuous wave stored on a hard drive. It's a series of discrete samples taken 44,000 times per second. Each one a separate number, a separate bit pattern, a separate step, reconstructed into something your ears experience as smooth and unbroken. Every message you send, every photo, every video call, every algorithm that decides what price you see on a website, what loan you're offered, what job posting appears in your feed, all of it is discrete, separate, countable, built from pieces. The continuous world you perceive is reconstructed from discrete fragments so dense, so rapidly delivered, that the seams become invisible. Discrete mathematics didn't just describe the digital age. It is the digital age. It is the substrate everything runs on. And then there's the deepest question, the one physicists and philosophers are still arguing about. Is the universe itself discrete? Look far enough down, past atoms, past protons, past quarks, past anything we've measured, and you reach the Planck scale, a length of about 1.6 times 10 to the negative 35 meters, the smallest distance at which the concept of distance may even remain meaningful. Some theories of quantum gravity suggest that space itself is not a smooth continuum, but is quantized at this scale, that there are smallest possible chunks of space, and that asking what's between two adjacent chunks is like asking what's between two adjacent integers on a number line. Nothing. There is nothing between them. They're adjacent by definition. If this is true, and we generally don't know, then the universe is not an analog place using discrete math as a convenient approximation. The universe is discrete. Reality, at its most fundamental level, is not a smooth surface, but something more like a grid. Not a wave, but a sequence of steps. The smooth world we experience would be an emergent illusion, the aggregate of unimaginable numbers of discrete pieces behaving together, creating the appearance of flow, the way a film's individual frames create the appearance of motion, which means that the ancient choice Boole made to build a logic from only two values, true and false, 0 and 1, might not just be a clever engineering decision. It might be the deepest echo of what the universe actually is. I don't know if that's true. Nobody does. But the fact that we can ask the question at all, coherently, precisely, with mathematics sharp enough to point at it, that's something we owe entirely to the people and ideas we've been following all night. Let's go back to the beginning, one last time. Abone, carved somewhere in the hills between what is now Swaziland and South Africa. 20,000 years ago, someone made notches, one at a time, separate, countable, discrete. We don't know what they were counting. Maybe the moon, maybe livestock, maybe something we'll never understand. But the act of carving a notch, of turning the continuous experience of time into a sequence of separate marks, that was the first step in a journey that ends here, with you lying in the dark, receiving information from a server probably hundreds or thousands of kilometers away, encoded in bits, transmitted as pulses of light through glass fibers, decoded by circuits built from Boolean logic, rendered in pixels on a screen, and your brain processing all of this right now. Your brain is not doing it continuously either. Your neurons fire in discrete spikes, not a smooth wave, but individual cells switching on and off, like Boole's switches, like Shannon's bits, like notches on a bone carved 20,000 years ago. The electrical language of your own thoughts is digital. We are, all of us, counting creatures, living in a counted world, made of counted things, and the mathematics that describes all of this, the discrete, the separate, the particular, the step-by-step, was built over 20 millennia by people who were mostly just following their curiosity into the dark. The story of discrete mathematics is the story of humanity learning that the universe, for all its apparent smoothness, might be built from pieces, and that the spaces between the pieces are where all the meaning lives.